So welcome back once again to the enrichment classes. We are continuing our discussion regarding the problems of electrochemistry. So without further wasting time, let us go into the problems straight away. Today's problems will be mostly related to Faraday's law. So most of the problems today will be related to the Faraday's law. It will help to clear our concept regarding this particular law. So the first problem goes like this. A current is passed through two cells connected in series. Two cells connected in series. The first cell contains X NO3 whole thrice, and the second cell contains Y NO3 whole twice. Relative atomic masses of X and Y are in the ratio of 1:2. What is the ratio of liberated mass of X to that of Y? That is the question. Now, let us see how to tackle the question. So, I would like to ask every student to repeat the question once again. Now, the point is, how can we deal with this? So, before going into that, let us see these two cases. That is XNO3 whole thrice. That means probably it will give rise to X3 plus 3NO3 minus. Similarly, Y NO3 whole twice. So on dissociation it will give rise to Y2 plus 2NO3 minus. Having said that, we have generated one cation and both the cations. One is having 3 plus and another is 2 plus. Now, carefully see. We know that equivalent weight should be written as atomic mass by valency. We know that atomic mass by valency. So we can write equivalent weight of X is equal to A by 3. Let me tell you, we are choosing that X, the atomic mass is A, and for Y, the atomic mass is B. We are taking these two. So say, for an example, X is having atomic mass A and valency 3, while Y is having atomic mass. So what should I write here? Because the valency should be 2 as per this. Why have I written valency is equal to 3 and 2? Because it is very clearly indicating that X3 plus accepts 3 electron to give rise to X, and Y2 plus accepts 2 electron to give rise to Y. Carefully see this ratio. The atomic masses of X and Y are in a ratio of 1:2. So if for atomic mass of X, if it is equal to A, for Y the atomic mass is B, and B should be is equal to nothing but 2A. So here I should be writing, first you can write B by 2, which is equal to 2A by 2, which is nothing is equal to A. Now, at last, as per the Faraday's law, we know when the same amount of current is passed between two electrolytes connected in series, so we should be writing mass of A divided by equivalent weight of A is equal to mass of B divided by equivalent weight of B. Now, since this part is done, I think I can erase this part. Now, after getting all this, we should be writing according to Faraday's second law, according to Faraday's second law, we should be writing mass of X divided by, or you can simply write mass of X divided by mass of Y is equal to equivalent weight of X divided by equivalent weight of Y. It can also be written as the ratio of their masses divided by the ratio of the equivalent weights. It can also be written as mass of X divided by equivalent weight of X is equal to mass of Y divided by equivalent weight of Y. Both are correct, but we are choosing this one. So remember our target as per the given question, what is the ratio of the liberated mass? So we have kept that on the left hand side. Now so we can write mass of X divided by mass of Y is equal to equivalent weight of X. Now equivalent weight of X is A by 3 already, and equivalent weight of Y, that is A only. So we are getting this value as 1 by 3. So the ratio is 1:3, and that is the final answer for this particular question. So this is how it is to be solved. First of all, we have written Faraday's law, and as per the Faraday's law, mass ratio we have kept on the left hand side, and accordingly we have calculated on the right hand side. Now let us proceed for the next problem. Next problem is, it is also related to the Faraday's law, but it is more connected to the first law. Question is, a current of 2.0 ampere passed for 5 hours through a molten metal electrode. Through a molten metal electrode, or you can write molten metal salts, deposits 22.2 gram of metal. Atomic weight is 177. Now the question is, what is the oxidation state of the metallic salt? What is the oxidation state of the metal in metallic salt? So this question, as you must have realized, it is mostly related to the Faraday's first law. So first thing first, let us calculate Q. Q is equal to I into T, and I, as you could see, it is 2 ampere multiplied by, it is passing for 5 hours, so it should be 5 into 60, that is minute. Now it should be further multiplied by 60, which is seconds. So this much coulomb. Calculate this much. If you calculate, you will be getting, see, it is 6 into 6, 36, 2 0, and 5 into 2, another 0. So it should be 36,000 coulomb. So according to the question, this much of current, if it is passed for 5 hours, it deposits this much of metal. So what we can write is, that we have to find out the oxidation state of the metal. So best way to do this is to calculate that how much it will deposit when I will pass 96,500 coulomb. Because for this particular metal, as per the question, the atomic weight is already given. We have to find out only about the oxidation state of the metal in this metallic salt. So what we can write is, we can write that 36,000 coulomb will deposit how much? 22.2 gram of metal. 1 coulomb will deposit how much? 22.2 divided by 36,000 gram. And let us find out the equivalent weight. So we are trying to find out for 96,500 coulomb, it will deposit 22.2 divided by 36,000 into 96,500 gram of metal. Calculate this much. Calculate this. If you calculate, you will be getting 59.5 gram. Remember, so this can be treated as the equivalent weight. So we can now write that the equivalent weight of metal is 59.5 gram. Atomic weight is already given, which is 177. Now we know that equivalent weight is equal to A by V. So V should be A by E. So that means 177 divided by 59.5, almost equal to 3. We are getting valency as a whole number almost equal to 3. So the valency will be 3. So that will be the oxidation state, this one, because the valency of this metal will decide its oxidation state. So just to repeat the process, we are initially finding out how much total electricity was passed. So as according to the question, that much of electricity will deposit 22.2 gram. So in order to find out the equivalent weight, we are passing 1 Faraday or 96,500 coulomb, that will deposit 59.5 gram. So now we are finding out the equivalent weight because the atomic weight are already given. So according to this formula, we are finding out valency, and from valency we can say what should be the oxidation state. Since it is metal, so it should be, oxidation state should be always plus 3. That should be the answer. Next question is related to the Faraday's second law once again. So first let me write down the question. The question is, carefully see, same quantity of electricity was passed through solutions of the solutions of salts of elements A, B and C with atomic weights 7, 27 and 48 respectively. The masses of A, B and C deposited were the masses of A, B and C deposited were 2.1 gram, 2.7 gram and 7.2 gram respectively. The valency of A, B and C. What is the valency? We can write what are the valencies of A, B and C. So I think you must have realized this problem is related to the Faraday's second law. So while solving this, first of all let us see, are they connected in series? You can see the same quantity of electricity was passed through the solutions. So they must be connected in series. So suppose, say, valencies of A, B and C. For A the valency is A, for B valency is B and for capital C the valency is small c. We are taking this. Then the equivalent weight will be, so equivalent weight, I should write the equivalent weight will be atomic weight divided by valency. We know that. So now if we want to find out the masses deposited are given, if we want to find out their valencies like this, we can write like this as per the Faraday's second law, that mass of A divided by equivalent weight of A. Similarly, mass of B divided by equivalent weight of B is equal to mass of C divided by equivalent weight of C. This second law explanation or second law mathematical output will help us to solve this particular problem. Now one by one. Mass of A, how much is deposited? 2.1 gram. So I am writing 2.1 divided by equivalent weight of A, that is atomic weight is given 7 divided by valency. So valency we have chosen as A. I hope you are getting my point. So this part is the equivalent weight, this part is the equivalent weight, is equal to mass of B. How much? For B it is 7.2 gram. Equivalent weight, atomic weight by valency, it should be 27 by B, like that. And the third one, sorry, it is 2.7. Third one is 7.2 divided by, it is written as 48 by C. So after simplification, if you simplify this, you can see it is 7. If you multiply it 3 times, it will be, I can write this one as 0.3 into A is equal to, here you can see 0.1 into B is equal to 0.15 C. So if I take these two only, I can say that it should be 3A is equal to B is equal to 1.5C. So obviously, if B is equal to 1, then A should be 1 by 3. So C should be 2 by 3 then, according to this mathematical output. So ratio of A is to B is to C, which ratio? We have to find out that valencies, ratio of valencies, because A, B and C are basically the valency of A, capital B and capital C. So if we are finding out the ratio of small a, small b and small c, basically we are finding out the ratio of the valencies. So it will be like A is 1 by 3, B is 1 and C is 2 by 3. So we are getting as 1 is to 3 is to 2. So this is the final answer for this particular question. Very good problem, I would say. We have just used Faraday's law. We have taken the valencies as small a, small b, small c. We have put the formula, we have simplified, and we have got the ratio of A, B and C. This is how this type of problem should be dealt with.